Hello, so good morning everyone to those who are watching my video during the daytime, and good evening to those who do so at the evening. So I am Charlie Dagoy, and for today I will be discussing to you the very last topic that we are going to cover this semester. So basically, I'm not only the last reporter for this group, but I am the last reporter for this class. So I hope that you will listen to me until the end and learn something. So as what you can see on your respective screen, so these are the topics that we are going to discuss later on. So of course, the very first one is for us to define what elastic waves are or what elastic wave is. So the second and third topics, it is related to the concept or to the concepts of elastic waves. So to this, we will be able to know the presence or the behavior of elastic waves depending upon the compressibility of the fluid or the compressibility of the matter, and then we will also be able to know the behavior or how elastic waves behaves or how elastic waves occurs if there is a disturbance that is exerted or that happens within that matter or fluid. So without further ado, let's start our discussion. So, of course, before we will be able to dig deeper on what elastic wave is, so the very first step that we are going to do, or the very important concept that we should do, is to define what wave is. So, what is wave? So, a wave can be defined as the disturbance produced in a medium that carries energy without a net movement of particles, and it is also defined as an oscillating flow or movement of energy through a medium such as space or mass. So I know that every one of us already know what wave is, no? Where in fact, one of our subject, which is the mathematics in the modern world, we're able to introduce us what wave is. So once again, what wave is? So, bet that you will answer that wave. It involves disturbances in the medium. So, if you were able to think of these phrases, then you are right. So, wave, of course, it is generated. It is because there is a disturbances that is exerted, or there is an external force that is exerted in the medium, which made it be vibrated, and that vibration, it is known to be as the wave. So of course, if you're talking about wave, it would not be possible without medium. So even the two meanings or the two definition of wave on your respective screens, it always repeat that wave is present in the medium. So it could be a space or a mass. So if we're talking about space, so light, something like that. There is a space, and then that will be the medium in which the light wave will occur. And of course, the mass. So if we're talking about the mass, these are the fluids and also the solid. So as what you can see on the illustration, so these are the parts of the wave. So if that quantity do have a wavelength, if it has an amplitude and the one oscillation, so that basically means that it is a wave. So we will be elaborating, or we will further elaborate these parts later on. So remember, no? So on the first slide for our lesson proper, there's these phrases, or there is this sentence in which wave is defined as the disturbance produced in a medium that carries energy without a net movement of particles. So without a net movement of particles. So what does this mean? So example for this is the experiment of the polystyrene beads, in which it is bathed in a basin of water. So what it was done in here is that, as what I've stated, it is bathed in a basin of water. So there is an external force that is applied to the basin of water, which make it be able to generate wave. So as what it has been observed, the polystyrene beads does not move or does not displaces the same displaces to the movement of the wave. So what it was meant is that, say for example, the external force is being applied to the left, or yes, to the left, and then as it has as a person, say for example the person pushes the basin, so the wave moves to the right. So what it was observed in there, na instead of the polystyrene beads moving along with the wave, it simply vibrates, or it simply moves up and down to up and down as the wave undergoes. So that means, or that concludes, that wave carry energy, not matter. So we will, if we are going to consider these beads as particles, so these particles, when there is a wave, so they will not be displaced, or they will not move to the direction where they or they will not be displaced to in a single, say for example there are series of waves, right? So they will not go along with them, but instead they will vibrate on their resting position. So they will just transfer energy from their neighboring particles, but they will not they will not displace from one place to another. So they can move up and down, or left side to side, but they will not be displaced from one place to another. So a simple example for this is, say for example, the cruise, or the ship that is kanang gi ano na gi parking. So the ship that has been parked, they even though there is a big wave, so dili man sila move from one place to another, so they will just simply vibrate in accordance to the movement of the wave. So say for example the wave moves forward, so instead of them displacing they will be displaced in a forward manner. They will just simply move up and down. So let us consider the shape as the particles. So that's how the particles of the medium behaves when there is a wave. So they will not dili sila mo move forward, or dili sila mo move backward the same movement as the wave, but they simply vibrates to their respective positions. Okay, so as we were able to define what wave is, so what wave is again? You cannot answer, but wave, it is the disturbance that happens in the medium, and it carries energy without the net movement of the particles. So for the elastic waves, an elastic wave generally travels through a material or fluid or on its surface without causing any permanent structural or physical changes. So it is sabotable man know that even though there is a disturbance in the medium, so that does not changes the composition of the medium. So if the medium is water, so even though there is a wave, it will remain as a water. So if there is a wave that happens in a solid in a metal, so that metal will remain as a metal. So there is no physical changes. So waves that propagate through water, sound moving through the air, as well as energy moving through solid materials such as the earth, are often described as elastic waves. So the water waves, the sound waves, and the seismic waves. So that seismic waves occurs when there is earthquake. No, so these three examples are known to be as the elastic waves. So how about the koan? So diba, as what it was stated that water wave propagated through water, sound wave propagated through the air, the seismic wave propagated through the earth. So these water, air, and earth. So what are these? What are these? So if ang katong tulo, the three waves are elastic waves. So what are these? What are the water, air, and earth known as? So these are called the medium or the elastic medium. Okay, so what is medium? Medium, these are the substance through which a wave can propagate. So as what it was stated earlier, that water waves propagates, or water waves happens in water, or they undergo, or they moves through the water. The sound waves moves or propagates through the air, and of course the seismic wave to the earth. So medium and elastic medium is the same thing. So this refers to the substances in which a wave can move or can propagate. However, elastic medium, so this already tackles about the characteristic of the medium. So not all the medium are elastic. So how can we tell that the medium is considered as an elastic medium? So if the medium can change its shape when any deforming force is applied, and later on come back to its original shape when the deforming force is removed, so these are known to be as the elastic medium. So example for this is when we throw or hagbungan nato og kanang pebble or a stone bakaha, we will throw it to a pond. So what will happen in there? So the water will of course undergo wave. So after a minute, what will happen to the water of the pond? Diba, it will return to its original shape. So after it so say for example, as we throw a stone on the pond, so there is a deformation to the medium, which is the water. So after when there is a deformation, later on it will come back to its original shape when the deforming force is removed. So after the deforming force, which is the stone, the thrown stone, the original shape of the medium, which is the water, comes back to its original one. So with that, water is known to be as an elastic medium. So the properties of elastic waves are influenced by the elastic properties of the propagation medium. So we know that the mediums, which are the air, the water, or the earth, do have different compositions, or they do have different characteristics. So with that, the properties of elastic wave also differs to depending upon to what property do the medium possess. So the example that we had earlier involves liquid, no? So in gas, so gas is an elastic medium, so since if it is compressed and the pressure is then released, it will regain its former volume, and the sound that is transmitted through a gas is an elastic wave. So the same thing as the liquid, no? So after the deforming force, so after it has been released, or if the deforming force is not applied anymore, so the properties of the gas returns to its original one. So say for example, let us consider this as a container that has been pressed by a bar. So considering that of course there's an air in there, so say for example, if you're going to press the bar to the container, so the property of the gas changes. So from a high volume, it will the volume of the gas will decrease, and then the pressure increases. However, when the deforming force, which is when we press the bar to the container, has been removed, so the volume of the gas returns to its original quantity, and then the pressure also will return to its original quantity. So that this indicates, or this concludes, that gas is an elastic medium, since after the deforming force is removed, the shape or the composition of the medium returns to its original one. So Of course, since we involved air in there, in here, or gas is also considered, I mean, air is considered as gas man, no? So there will be a sound that is transmitted in here. So what if the gas is an elastic medium? So what is the sound again? Or what is the sound wave in here? So it is the elastic wave. So that is for the elastic medium and elastic wave. So in synthesis, so an elastic wave is produced, of course, as what it has always been told, that elastic wave occurs, it is because there is a disturbance that is produced at a point in a medium. So if we're talking about a medium, this involves the spaces, the solid, the liquid, the gas, or anything in which the elastic wave travels through. So the following that are in bullet are the characteristics of an elastic wave, or their behavior. So the very first one is that the disturbed particles interact with the particles in its neighbor, and its energy gets handed over the next particles due to the inertia of the medium. So what it is meant by there. So let us bring back our example earlier, which is the koan, which is when we throw a stone in a pond. So what happens in there again? So there is a wave that is generated since there is a disturbance that is applied to the medium, which is the water. So if we are going to observe the waves of the water, is there only a single ring? So usara ba ang ring sa wave? There only one wave that is generated in there? Diba dili? So there are series of spherical shape nga waves. So this explains the first behavior of the first concept of an elastic wave. So it is because since the disturbed particles interact with the particle in its neighbor, so say for example this is the starting point of the wave. So the particles in here, they interact with the particles in its neighbor. So that means there is another wave that is generated. So that this indicates that the particles on the starting point interacts with its neighboring, and then its energy then gets handed over to the next particle. So that made the series of waves to occur. So there's no only a single wave, that there are series of waves. So this means that the particle of the starting point, or the particles interacts to another particles, and then that means that they handed energy, so that neighboring particles also undergo waves. So the second concept of elastic wave is that the disturbed particles come back to the equilibrium position. So as what I've stated earlier, no, after the deformation, it will come back to its original shape. So as what it was stated also, as what elastic wave has defined, it involves the disturbance of the medium without a physical change. So that means the water will remain as water until the after the wave after the wave happens. So every harmonic elastic wave is characterized by the vibration frequency and amplitude of the particles of the medium, phase and group velocities, a wavelength, and the distribution of displacements and stresses over the wavefront. So on this statement, given the parts of the elastic waves has been mentioned man, no? So we are going to further elaborate, as what I've said earlier, we are going to further elaborate it later on. So let us focus to the statement, to where it states that every elastic waves has the distribution of displacement and stresses over the wavefront. So let us talk about wavefront. So wavefront is an imaginary surface representing corresponding points of a wave that vibrates in unison. So considering the image of a circular waves and a plane waves given, so that points in a single phase of wave is called the wavefront. So another definition for us to follow on what wavefront is that it is the set of all locations in a medium where the wave is at the same phase. So wavefront is useful for showing how waves move in two dimensions. So since wavefront is composed of points of oscillations of the waves, so it visualizes the orientation of the movement of the wave. So as what I've stated earlier, diba, wavefronts do have three types. So namely the spherical wavefront, the cylindrical wavefront, and the plane wavefront. So the very first type of wavefront is the spherical wavefront. So wavefront that appears as spheres centered on the origin are known as spherical wavefronts. So based on the definition given, so relate it to the image that you've just seen on your respective screen. So as what you can see, it is water ripples, no? So there is a water droplet that is dropped to the water, and then there is that center of origin, then have a succeeding wave. So how do the movement of the waves of the ripples of water be considered a spherical wavefront? So why is that so? So as what it has been defined, no? So the disturbance of the water to the water in the given example creates a spherical shaped wave. So it was able to point out the definition of the wave of the spherical wavefront. So that indicates that that the water ripples is a spherical wavefront. So imagine or just refer to the image given that you dropped a stone in the water. So that area to where the stone drops is called the origin. So since one of the characteristic of the elastic wave is that it disturbs its neighboring particles, so it will create waves after a wave. So the shape of the wavefront depends on the shape of the source of the disturbance. And since the orientation of the disturbance is spherical, when the stone is dropped, the origin is then shaped, or the origin do have a spherical shaped orientation. So because of that, it also creates a wave that are also spherical. So the point of oscillation of a single phase of the wave here that forms a concentric rings or spheres is described as the spherical wavefront. So that is for the spherical wavefront. So another type of wavefront is the cylindrical wavefront. So on a cylinder's curved surface, so there are all locations that are equal to the distance from the source. So as a result, the wavefront has a cylindrical shape. So in simple terms, we get a cylindrical wavefront from a linear source of light. So example for this is when the rays of light falls on a lens after coming out of the lens, so they will converge at the points. So the waves are bending and converging at the point, so the shape of the wavefront is in the form of cylinder. So that is for the cylindrical wavefront. So you can refer it to the image given, diba? So there is a linear source of light, so there will be an equal distribution of waves that has been generated because of the source of light that is oriented into a linear way. So the last type of wavefront is the plane wavefront. So in plane wavefront, the wavefront will appear as a plane when viewed from a considerable distance from a source of any kind. So example is the image given, which is the ripple tank. So the source of light is distant from the medium, right? So nadiri ang the ripple tank is here, and then the source of light, which is the bulb, is way farther from the ripple tank. So considering that the base of the tank is transparent, so as what you can see, there it is transparent. So what can you observe here is that the wave's oscillation can be seen distant from the source. So the wave is in the ripple tank. However, you can see that there is you know you can observe that the wave's oscillation is seen distant from the source. So this concludes the plane wave front. So plane wave front is defined as when a small part of the spherical or cylindrical wavefront originate from a distant source like infinity, then the wavefront which is obtained is known as a plane wavefront. So we should always remember that the source of light or the source of the wave in a plane wavefront is distant from the medium. So aside from the ripple tank that we've just be considered as an example for the plane wave, so what are the other examples of plane wave front? So the other example for this is the rays of the sun. So as what we've observed now, since the plane wave front occurs when the source of any kind is distant from the medium, then we can consider the rays of the sun as a plane wave front, since the source of the wave, which is the sun, is very far man, no? And then we were able to obtain the wave that has been generated because of the source of light. So this wave that has been created by the source of wave, these are called as the plane wave front. So on this part, the plane wave front in here is the rays of the sun. So as we're all through with the wave front, so let us bring ourselves back to the elastic wave. So what is elastic wave again? So it is a wave that is produced due to the disturbance produced at a point in the medium. So the disturbed particles interact with the particles on its neighbor, and its energy handed over to the next particle. So that explains why there are series of waves generated after the point of origin. So with that, I will introduce to you the different types or kinds of elastic wave or waves. So the two are the transverse waves and the longitudinal wave. So in transverse waves, so as what you can see on the example illustration, so the person or the people at the center moves upward, and then that there is an orientation of the wave in there in which it moves from left to right. However, even though the wave moves from left to right, the people in there moves upward. So in longitudinal wave, however, so the same orientation as the first as the wave on the transverse wave, so the wave also moves from left to right, and then the people at the center moves parallel or moves the same orientation as the vibrated the same orientation as the movement of the wave. So based upon the illustration given, so what are the distinction between transverse and longitudinal waves? So how are they different with each other, just depending upon the illustration given or the explanation that I've said earlier, that the first wave, the people moves upward, and the second wave, the people moves the same orientation as the movement of the wave. So diba, as what we've observed in transverse waves, the three people, not the three people, but the people at the center, which are known to be as particles, moves upward. So this indicates that transverse waves cause the medium to move perpendicular to the direction of the wave. So transverse wave, in other words, transverse waves are those waves in which the particles of the medium moves perpendicular to the motion of the wave. So longitudinal wave, on the other hand, as what we've seen on the illustration, so the people moves on the side. So but as what I've said, the orientation of the wave is that its motion is sideward also, and then the people at the center, which are known to be as the particle, also moves at the side or sidewards. So considering the movement of the wave, I mean, considering that the movement of the wave is horizontal, so this indicates that longitudinal wave are those wave in which the particles of the medium moves parallel to the motion of the wave. So if you were able to observe what I've just said, so you are right. So that is the difference between the transverse waves and the longitudinal wave. So first, let us further elaborate on what transverse waves is. So transverse wave, it is a wave in which the particles of the medium move in the direction perpendicular to the direction where the wave moves. So as what you can see on the illustration, so the direction of the particles of the medium of propagation of waves is perpendicular to the direction of the wave. So instead of moving sidewards, the same orientation as the direction of the propagation of the wave, the particles in a waves that is transverse moves upward. So that means since the wave moves sideward and then the particles moves up and down, then it has a 90-degree orientation. So that is one thing we can base or we can remember of if we think of transverse wave. So it creates a 90-degree orientation because of the movement of the particles and the movement of the wave. So instead of vibrating the same direction as the wave, it moves up and down. Okay, so for us to understand more about transverse wave or the behavior of the particles of the wave that makes it be considered as a transverse wave. So let us refer to the GIF on your respective screen. So what can you observe? So the particles moves up and down, right? And considering that there is an external force applied on the left end, so say for example there is an external force in this part, or let us imagine that this is an ocean wave. So the energy will then transfer to the right side. Hence, the particle should also vibrate along with the orientation of the energy. However, with transverse waves, as what you've seen on the illustration, it made the particles of the medium to move perpendicular to the orientation of the wave movement. So the animation shows a one-dimensional transverse plane wave propagating from left to right. So the particles do not move along with the wave. They simply oscillate up and down about their individual equilibrium positions as the wave passes by. So that is for the transverse wave. So for us to repeat, so transverse waves are those waves in which the particles of the medium moves perpendicular to the motion of the wave, to the motion of the wave. So as what you can see, so transverse waves do have parts. So and this is not only for the transverse waves, but this is also applicable for the longitudinal wave or any types of waves. However, this is common, or this is an important part for us to this is an important composition of the transverse wave, since it really reflects the movement or the typical movement or the typical form of a wave. So the very first one is the crust. So the crest is the highest point of a transverse wave. So as what you can see on the on the illustration, there is a label in there, namely the crest. So that is the part of the of the wave. So say for example, if we are going to think of a curve. So that point, that highest point of the curve, that is the crest of the wave. So the second one is the trough. So the trough in there is the lowest point of the transverse wave. So if we have the highest point here, we also have the lowest point, and it is named as the trough. So there's also based on the illustration, there is a label in there, which is the trough. So we will have a intersection. Is this an intersection? A union. So in mathematics, crest is the intersection, the highest point of the intersection, and then the trough is the lowest point of the intersection and union. So union katong relation. So the third one is the wavelength. So wavelength is the distance between one point of a wave and the nearest point just like it. So from a single wave, we will make it two. So diba the highest point of the wave is a crest man, no? So if we are going to label crest to each of the waves, so that distance between them is the wavelength. So the next one is the amplitude. So it is the maximum distance the wave vibrates from its rest position. So it is a measure of energy carried by the wave. So the amplitude, so it is how high the koan is, how high the wave is. So as ang amplitude ko, no, it is a measure of energy carried by the wave. So the relation between amplitude and energy is that when the wave to when the transverse wave, or when a wave do possess a high energy, then the amplitude is also high. So that means amplitude and energy is directly proportional to each other. So if there is a low energy, there is also a low amplitude. Okay, so as what you can see, that that already explains what I've said earlier, no, na the high energy waves have high amplitude and low energy waves have low amplitude. So on the first on the first wave, so it has a low, diba, the amplitude in there is how high the how high the wave is. So since the wave in here on the left side is low, so that means it has a low amplitude. So low amplitude, that means the wave do have low energy. So well, the second one, so there is a high amplitude, no, so that indicates that the wave do possess a high energy. So kanang kuan, the second illustration, so which of these waves has a larger amplitude, or let's just say the largest amplitude? No, it's pretty obvious that it is in the third wave, no, because it has it is tall. So if we're talking about amplitude, it is how tall the wave is, or it is the maximum distance the wave vibrate from its rest position. So that means it has the highest energy among the three waves. So longitudinal wave, on the other hand, is a wave in which the particles of the medium move in the direction parallel to the direction in which the wave moves. So if the transverse waves, if the waves in transverse waves moves, I mean that its particles, or the particles to the particles of the medium to where it travels, moves perpendicular to the direction of the wave. So in longitudinal wave, they move or they move parallel to the movement of the wave. So that means they move or they vibrated along with the motion of the wave. So that is the difference between longitudinal wave and transverse wave. So as what you can see on the illustration, so considering the blue dot, that the blue dot represents the particles. So the particles is what? It moves parallel to the movement of the wave or energy, right? So that is longitudinal wave. So there is we also have this GIF for the longitudinal wave. So as what you can see, the longitudinal waves displacement is parallel to the direction of the wave propagation. So the animation shows a one-dimensional longitudinal plane wave propagating down a tube. So the particles do not move down the tube with the wave. They do not move up and down. So they simply oscillate back and forth about their individual equilibrium position. So the matter or the the illustration still applies the rules. Applies the concept of elastic wave, in which the particles do not move from one direction to another, or does not go along with the displacement of the wave. So they simply oscillate on their respective position. So in this case, in longitudinal wave, they move back and forth. So that means they go along with they vibrated along with the movement of the wave. If we pick a single particle and watch its motion, so the wave is seen as the motion of the compressed region or the pressure wave, so which moves from left to right. So the second animation at right shows the difference between the oscillatory motion of individual particles and the propagation of the wave through the medium. So the animation also identifies the region of compression and rarefaction. So we later on we will be going to elaborate what compression is and what refraction is. So as a background or an initial insight, so the rarefaction in there is the the kanang buwag nga version sa wave, while that protruding black line, so that is the compression side. Okay, so we were able to encounter the word compression and rarefaction no, basing upon the GIF that we've just seen as an example for the orientation of the particles of the longitudinal wave. So what is compression and rarefaction di? So first is the compression. So as what I've stated earlier, it is the part of the wave or that GIF, that protruding black part, a black line, so that is the compression. But however, we're not able to know the reason behind them. So I guess all of us will just simply say that it is the crust of the wave, but it is the compression. So compression is the region in compression wave or in longitudinal wave where the medium becomes crowded together and more dense. So that wave will be crowded in a single phase. So rarefaction, on the other hand, it is the less dense region of a compressed or a longitudinal wave. So as what I've said earlier, it is the gap. It is katong less black na part sa illustration. So that is the difference between the compression and the rarefaction. So a good example for this is the string of the guitar. So diba, if you're going to pluck the guitar, so the air in there will be compressed, or even the strings will be compressed. So there is a time where they become bonded, or the waves become bonded, and there is also the time where the waves on the strings are not compressed anymore. So that is a good example for compression and rarefaction. And of course, there is a wavelength. I guess there it won't be called as a wave if there is no wavelength, of course. So the wavelength of a longitudinal wave can be measured as the distance between the center of two compressions or rarefactions. So in transverse waves, diba, the wavelength if in there are the distance between one wave to another. However, on this wavelength, however, the wavelength of a longitudinal wave, it is the distance between the center of two compressions or refractions. So say for example, this is a compression site. So we will find, or we will locate the center of it. So if the neighboring, we will also locate the center of the neighboring compression site of the first compression site, and with that, and the distance between them, the distance between the center of the two compression region, so that is the wavelength of the longitudinal wave. So next is the amplitude of the longitudinal wave. So the amplitude of a compression or longitudinal wave is related how tightly the medium is pushed together in compression. So the arrows that you've just seen on the illustration, so that is the amplitude of the wave. So it is how tightly the medium is pushed together in compression. So if the particles of the medium are tightly packed with each other, that indicates that it has a high amplitude. Hence, since it has a high amplitude, so that indicates that the wave do possess a high energy. So we already know what wavelength, no? So it is the distance between the neighboring waves. So in longitudinal, it is the distance between the center of the neighboring compression region. So based on what you've just understood on what wavelength is, so which one of these waves, or which one of the two waves, has a larger wavelength? So since this neither indicates whether the waves are transverse or longitudinal, so pretty obvious that the second illustration, or the second wave, is the wave that has a larger wavelength. So it's pretty obvious with the distance between the two waves. Next is the wave frequency. So wave frequency is the number of wavelengths that pass a fixed point every second. So when frequency increases, wavelength decreases. So if we're going to refer to the first illustration, kanang above, when I ask you which has a larger wavelength, so the first wave is what? What is the frequency on the first wave? Diba? It has a high frequency, since it has a lesser wavelength. So since, as what it was stated in here, that when frequency increases, wavelength decreases. So that means frequency and wavelength is inversely proportional with each other. So that means if the first quantity is getting high, so that means the second interconnected quantity will be getting low. So just like the illustration that is related to the wave frequency, no? So on the first illustration, it has a low, it has a shorter wavelength, so that means it has a higher frequency. So meanwhile, on the second illustration, or the second wave, since it has a larger wavelength, so that means it has a lesser frequency. So frequency, once again, it is the number of wavelengths that pass a fixed point each second. So the SI unit for the frequency is hertz, or can be written as the symbol of Hz. So a hertz is one wavelength passing by a fixed point per second. So based on the illustration given, so based on your understanding on what frequency is and how and its relationship between wavelength, since we can connect wavelength to assess how high or how low frequency is of a wave. So which one of these waves has a higher frequency? So obviously it is the second, the second or the first. Also the first wave. So since it has a lot of wavelength that is passing per second, and also they are tightly packed with each other, so that means it has a lesser wavelength. So if there is a shorter wavelength, so that indicates that the wave 2 possess a high frequency. So always remember that wave frequency and wavelength is inversely proportional with each other. So given the illustration on your respective screen, so these summarize the motion of the transverse and longitudinal wave. So on the first on the wave A, so what do you think is this type of wave, or to where it can be classified as? Is it a longitudinal wave or a transverse wave? So obviously no, there is a compression site and there is a rarefaction site. So if there is a compression site and rarefaction site Tagani, so that means that the wave is a longitudinal wave. And of course, and also the orientation of the wave, in which the direction of the disturbance and the direction of the wave motion is parallel with each other. So the disturbance vibrates the same orientation as the direction of the wave motion. So the wave P is classified as a transverse wave. So why is that so? So from the arrow itself, no, it is perpendicular. So if we're going as what I told you earlier, that perpendicular, it forms a 90-degree orientation, or a 90-degree angle. So say for example, this is the wave motion from on this case, it is from right to left. So the direction or the vibration of the particles that is being disturbed is up and down. So that means up and down, and then there's something that intersects, so that the angle between them forms 90 degree. So that is for the longitudinal and transverse wave. So a synthesis, so we have here the table of the differences between the transverse wave and the longitudinal wave. So the very first one, obviously the wavelength, the amplitude, the crest and the draw is pretty obvious with in the transverse waves, So in longitudinal wave, the compression site and the refraction site is pretty obvious. So that the very first difference between the transverse waves and longitudinal wave are the orientation of the waves, on how the wave moves. So the second one is that the transverse waves, the particles in transverse waves vibrate in a direction perpendicular to the direction of the propagation of the wave. However, or meanwhile, in longitudinal wave, it vibrates parallel to the direction of the motion of the wave. So the third one is that transverse waves do have crests, and there is a crest and trough that are formed. However, in longitudinal wave, as what I've stated, there is a compression site and rarefaction site. So the fourth one is that transverse wave formed on the surface of solids and liquids, while longitudinal waves, it occurs, or it can be able to travel to any of the states of matter, namely the solid, the liquid, and the gas. So the fifth one is transverse wave can be elastic and non-elastic. So example for this is the light wave and radio wave. So in longitudinal wave, only elastic waves or mechanical waves, the example of longitudinal waves are those who can only be classified as an elastic wave. So example for this is the sound wave, the seismic wave, and the water wave. So the last difference between the two is that transverse waves do not create pressure difference in the medium, while the longitudinal wave creates pressure difference in the medium. So as what you can see on the very first difference between transverse waves and longitudinal wave, diba, the transverse wave do have a uniform orientation of their wave. So that means if the first wave behaves that way, so that means the preceding wave will also behave the same behavior as the first wave. However, in longitudinal wave, there is a rarefaction site, there is a compression site, so they are really different with each other, right? So that's all for the transverse waves and longitudinal wave. So as what you can see on your respective screens, so that is the wave equation. So the speed of a wave is equal to the wavelength times frequency, to where the unit for the speed, or the as a unit for the speed is meters per seconds, and then the unit for the wavelength is meters, and then the unit for frequency is hertz. So that basically means, like, say for example, if the given wavelength is in centimeters, so you have to convert it into meters. The same thing as the speed of the wave and the frequency. So this I've introduced to you the wave equation. It is because we will be using it for the problem solving for the speed of wave. So as what I've just said earlier, no, nga, if the wave is a longitudinal wave, so that means it is an elastic wave. So example of an elastic wave, as what I've stated earlier, and even on the first part of our discussion, these are the sound waves, the sound waves that propagates through the air, the water waves that propagates through the, of course, water, and then the seismic waves that propagates through the earth. But since we are talking about fluids in here, so that means we are going to cover the elastic waves that travels through the fluid. So as what we are always as what the reporters have always been discussing of, or always reminds you that fluids, so these are the substances that has the tendency to flow. So hence the example for this is the water, the liquid, and the gas. So that basically means we are not going to cover the seismic wave. So that explains on why we only covers the sound waves and the water waves. Some waves, like water waves and sound waves, are formed through the vibration of particles. So waves form because water molecules are disturbed, and sound waves are formed by the disturbance of air particles or particles in an object through which sound is traveling. So as different as they all seem, all of these waves have something in common. So they are all oscillations that carry energy from one place to another. So this basically just repeats the concept or the behavior of a wave. So what are the difference between the sound wave and water wave? So first is that the motion of particles in a sound wave is different than a water wave, in that sound waves travel through the air as a longitudinal wave. On the other hand, water waves travel in a transverse wave. So sound wave is considered as a longitudinal wave. It is because the orientation of the particles of the medium that it travels is moving side to side, or back and forth, that is parallel to the orientation of the motion of the wave. So on the other hand, with water waves, since basically it is a surface wave, so that means it will, so this considered even though it is considered as both transverse wave and longitudinal wave, but because water waves is known as carrying or is also known as a surface wave. So if we're going to talk about the surface, then the particles of the wave has the tendency to move up and down. So moving up and down, so that means it is a transverse wave. So we can just base on the illustration given now that the sound wave, it involves compression and rarefaction, and then the ocean wave, of course, it has a uniform wave that basically explains the behavior of a transverse wave, in which it in which that it do not create pressure difference in the medium, so it is uniform. So whereas in the longitudinal wave, so as you can see in the sound wave, there is a compression site and there is a rarefaction site. Also, sound waves are invisible vibrations that travel through the air, while water waves are visible ripples that moves through bodies of water. Of course, we cannot see sound waves man, no? And also, and of course, we can see water waves through ripples in a body of water. So sound waves travel at different speeds depending on the medium they are traveling through, while ocean waves travel at a constant speed on the surface of the wave. So this is the third differences between sound waves and ocean wave. It is because in sound waves, diba, it cannot only travel through the air, but it can also do so to solids and liquid. So that means depending upon the medium that it travels, so it really its composition or its behavior really differs depending upon to what medium it travels or it propagated. Meanwhile, if we're talking about ocean waves or water waves, can it propagates through solids or can it propagates through air? Diba not? So that means it will have a constant speed of the surface of the water. So that is the difference between the ocean waves and sound waves. So the fourth one is that sound waves have different frequencies that determine the pitch or tone of the sound, while ocean waves have a characteristic wavelengths and period that determine their height and frequency. So sound waves mainly uses frequency in order to assess its behavior, while in ocean waves we will be assessing its wavelength and period to determine their height and frequency. So the third one is that sound waves are caused by vibrations in a medium such as speaker or a person talking, while ocean waves are caused by wind, earthquakes, and other factors. It is mainly about the disturbances that may create that these are disturbances that creates them. So in sound waves, it is caused by the vibrations, and then in ocean waves, it is caused by the external forces such as wind, earthquakes, and other factors. Since we already know that sound waves and water waves are both elastic waves, and they do also have differences with each other in relation to their speed, their frequency, or their behaviors and the disturbances that created them. So let us further dig deeper on what these two are. So sound waves is a pattern of disturbance caused by the movement of energy traveling through a medium as it propagates away from the source of the sound. So this basically is a term for wave. So of course there is a disturbances that happens or that is exerted in the medium, which made the sound wave to exist. So in sound wave, it could be in the air, in the water, or solid matter. So kanang sound waves can travel to any matter except for vacuum, I guess. So why is sound wave a longitudinal wave? So I've already explained this to you earlier, no, on why sound wave is a longitudinal wave. Example for this is when you pluck a guitar string. So it begins to vibrate from side to side. So side to side, that means it is parallel to the orientation or to the movement of the wave. So the air particles around the strings apply the compression and rarefaction orientation, which is the characteristic of longitudinal wave. So aside from this, the string moves parallel to the motion of the sound wave. So if there is compression and rarefaction na gani nga that happens in a medium, so that automatically means that it is a longitudinal wave. So a good example for this is, as what you've observed, if you're going to pluck the guitar string, so there will be some of the air particles will be they will be compressed, so as you pluck the guitar, and then if you are going to release it, so there will be a particles that will not compressed, or yes, there are part in which the particles are not compressed enough, so that is the rarefaction. So that basically that concludes that sound wave is a longitudinal wave. So as what I've said earlier, sound waves travels at any states of matter or phases of matter. So that means it can propagate in air, it can propagate in water, it can propagate in liquid. So the question is, what will be the behavior of the sound wave if it will be going to travel at different matter? So what will be the behavior of the sound wave if it travels through a solid? What will be its behavior if it will be going to travel or propagate in a liquid and in a gas? So this basically talks about the speed. So how fast the sound wave travels depending on the medium that it travels. So the very first one is the speed of sound in solid. So what will be the speed of sound in solid? So will it travel slow, or will it travel the fastest? So solids are significantly denser, so that means it is the mass over the volume. So it basically the very close term that we can associate with this is the weight. So how packed solid is. So solids are significantly denser than liquids or gases, and this means that the molecules are closer to each other in solids than in liquids, and liquids than in gas. So this closeness due to density means that they can collide very quickly. So due to this, the velocity of sound in a solid is faster than in a gas. So since the particle of the solid are tightly packed with each other, so that means they can collide very quickly. So basically the sound will be able to travel fast. So the speed of sound in liquid, on the other hand, so similarly, the density of a liquid is greater than the density of a gas. Therefore, the distances between molecules are more in liquid than in solids, but are less than in gases. Hence, the speed of sound in liquids lies in between the speed of sound in solids and gases. So basically, the denser the matter or the denser the medium is, the more likely the faster the sound wave will travel. So in liquid, so it has a it is loosely packed, or the particles of the liquid is loosely packed with each other compared to solid. So that means it is less dense than the solid, but it is denser than in liquid. So that means it lies between the speed of sound lies the speed of sound in liquid lies in between solids and gases. It is because sound travels faster in solids than in liquid, but the sounds the sound travels faster in liquid than in gases. So basically, compared to the three matter, it is the second medium in which liquid can travel fast. So how about in the speed of sound in gas? So since compared to the first two, the particles of the gas is loosely packed with each other, so that means it can barely they cannot be able to collide very quickly with the sound. So that means the speed of sound is lesser in gas. So yeah, so so the speed of sound really depends upon to what medium it travels through. So in solid, it travels the fastest. In liquid, it travels faster. But in gas, it travels the slowest. So let us talk about the factors affecting the speed of sound. So there are factors that affects the speed of sound aside from the medium. So of course, the density, and the additional one is the temperature. So the density and temperature of the medium in which the sound wave travels affect the speed of sound. So in terms to the density of the medium, as what it was stated earlier, when the medium is dense, the molecules in the medium are closely packed, so which means that the sound travels faster. So therefore, the speed of sound increases as the density of the medium increases. So since the solid do have the greatest density among the three states of matter, that basically means that solid travels the fastest in this matter. So the next one is that since since liquid has a closer the particles of the liquid is more packed than in gases, so that means sound waves travels the fastest in there compared to gas. So in terms to the temperature of the medium, so the speed of sound is directly proportional to the temperature. Therefore, as the temperature increases, the speed of sound also increases. So a good example for this is when like the kettle, no? 'Di ba? If the water in the kettle do already have the greatest temperature, diba? There will be a pressure in there, and that pressure wanted to escape from the kettle. So that is the reason why kettle makes sound when the water is already ready. So that is the example for the temperature of the medium. So the speed of sound is directly proportional to the temperature. So when the temperature is increasing, then the speed of sound also increases. So if there is a low temperature, the speed of sound is also low. So in density, it is also directly proportional, because the denser the medium is, so the faster the faster the sound wave will travel. So I've just introduced to you the formula for the speed of wave earlier, right? So since the speed of sound is the distance traveled by the sound wave in a given time, so the speed of sound can be determined by the following formula. So V is equal to that symbol times frequency, where V is the velocity, or is the velocity. That symbol is a wavelength, and the F is the frequency. So here is as what you can see in your respective screen. So these are that we do have a sample problem solving here. So it is, how long does it take for a sound wave of frequency 2 kilohertz and a wavelength of 35 centimeter to travel a distance of 1.5 kilometer? So I already reminded you earlier, no, nga the SI unit for the speed of wave is hertz, and then the SI unit for the wavelength is meters, and then the SI unit for the speed of wave is meters per second. So if you were able to observe that there is a unit that is different from the SI unit of the given quantity, so what you're going to do is to convert it to the desired SI unit. So just like what you've seen early, as what you can see on the slide, no, on your respective screen, the kilohertz on the problem is already converted into hertz, and also the centimeter into meter. So in one centimeter there is 100 meter. So if you are going to convert 35 centimeter into meter, then you will be able to obtain a result of 0.35 meters. So as the hertz, so in 1 kilohertz, there is 1000 hertz. So since the given is 2 hertz, 2 kilohertz, then we will be multiplying it by 1000 hertz. So 2 times 1000 hertz, so we were able to obtain the quantity that you've just seen on your respective screen, which is the 1000. So the very first thing that we are going to do is to find the speed of sound. So we were able to obtain 700 meters per second. So since we already have this formula, we already have this result, or we already have the velocity, so we will be going to find the time taken by the sound wave to travel a distance of 1.5 kilometers. Since we already have our velocity here, and we also have our distance here, so that means we can use the formula for the velocity, which is velocity is equals to distance over time. So since the time is not given in here, so since this is the quantity that we are going to seek for, so that is the reason why the formula is oriented in that way. So substituting the values in the equation, so time is equal to 1,500 meters. So convert the 1.5 kilometer into meters over 700 meters per second that we are just able to obtain, and then we will able to come up with the result of 2.1 seconds. So therefore, it takes 2.1 seconds for a sound wave with a frequency of 2 kilohertz and a wavelength of 35 centimeter to travel a distance of 1.5 kilometer. So that is for the problem solving for the speed of sound. So as we're all through with the sound waves, so let us move on to the water waves. So water waves are surface waves, and they are made of a combination of longitudinal and transverse waves. So it is depending upon the depth of the medium. So if we are going to refer to the surface of the medium, which is the ocean or the water, so that means, or transverse, the behavior of the transverse waves is commonly be observed on that part. However, if we're going to go deeper to the medium, so longitudinal wave exists on that part. So these waves are formed by the interactions of Earth, the Sun, and the Moon. So in our Earth and science, or in astrology. So water waves have crests and troughs. So the source of most waves on the sea surface is wind. So, diba, if the longitudinal wave or the sound waves, it do have compression site and rarefaction site. So in water waves, it has a crest and a trough. So so the firm explanation on why water wave is considered as transverse wave and longitudinal wave, it is because as what I've stated earlier, on the surface of water waves are formed, and the wave that is formed is a transverse wave. So as we go deeper inside the water, as we go deeper inside the water body. So longitudinal wave displaced parallel to the direction in which the wave travels. So it is basically about the orientation of the particles as the wave happens. So in surface wave, the up and down movement of the particles can be observed, and then as we go deeper to the medium, so there will be a back and forth movement of the particles. So that means how we consider water wave as depends upon to what area we are referring to. So the characteristic of a water wave, so we've already discussed this one, no, in transverse wave. So since water wave is mainly a transverse wave, so of course it has a crest, it has a trough, a wavelength, a wave height, a wave steepness, amplitude, and wave period. So the crest, as what we've discussed earlier, it is the highest point of the wave. The trough, which is the lowest point, and then wavelength, it is the distance between between the crest of the wave and the crest of the other wave, or its neighboring wave. So wave height, it is the height from trough to crest, so from the trough up until to the crest, so that is the wave height. So the wave steepness, it is the ratio of wave height to wavelength. The amplitude, which is the distance from the center of wave to the bottom of the trough. So you can just refer to the illustration on where you can see the following parts. So the wave period, it is the time for one full wavelength to pass a given point. So the following characteristics of water wave is these are important in order for us to determine the size of the waves, the speed at which they travels, or the height of the waves. So we will be going to use the following parts or the following characteristics of the water wave in order for us to assess on what the wave looks like. So is it a wave that has a low energy? Is it a wave that is, that has a greater frequency? So we will be going to we will be going to assess the wave using the following parts. We had the factors affecting the speed of sound waves, so we also have the factors in water waves. So the speed of water wave is determined by a number of factors. So first, the most important factor is the depth of the water, which shallow water generally allowing for fast wave speed than deeper water. So it's really, it's already sabotable no nga. The shallow water do have as faster wave speed than deeper waters. So the other factors affecting wave speed include the wavelength, the water temperature, and the presence of obstacles or obstruction in the water. So in water temperature, diba, we can refer to the water that we are boiling. So diba, there is a greater wave when the water is hotter. So that means it is directly proportional. So the speed of the water wave is directly proportional to the temperature of the medium. So if the medium is hot, then the wave or the speed of the wave is faster. So of course, also the presence of obstacles. So if there is an obstacle, something will really hinder the speed, or it will something will really hinder the phasing of the water waves. So the presence of surface tension and friction can also reduce the speed of waves, while wind and current can increase their speed. So we in our physics last senior high school, we were able to cover the friction. So example for this is when we are going to push a cabinet. So diba there is something like hindering us, or there is an obstacle which made us not be able to push the cabinet efficiently. So that that force or that hindrance is known to be as the friction. So it is in the since the surface in which the cabinet is being pushed do have a friction, so it really affects the speed, or it really affects on how the how the cabinet moves when we are going to push it. So same thing as the speed of waves. If there is a friction, then it's really more difficult for the water wave to travel through, since there is something, or that's something which is the surface tension and friction that hinders the speed or the phasing of the water waves. Also, of course, if there is a greater external force like wind and current, so that means the speed of an elastic wave is really will also, you know, will also be greater. So the next one is the shape of shoreline, the direction of the waves, and the amount of sediments in the water can also affect the speed of water waves. So the last one is the frequency of the wave source increases with its speed, which also increases with its frequency. So as a result, when a wave is generated, its speed increases. So if you want to learn more about our discussion for today, so we have complied all the resources that we have or that we've referred to in order for us to make a report. So it would not be possible without these authors, which introduces us about the concepts of what we've just discussed today.